Okay. Can you hear me on Zoom? Okay, good. Where is this thing? Okay, I think it's time to get started. We're going to continue talking about microarchitecture today. It's going to be fun. As usual, this is a Friday. I can tell whether it's a Thursday or Friday just by looking at who's in class. Yeah. You don't need complicated AI for this. It's a simple classification task, right? Okay, now that that's done, let's get started. Okay, so just reminders, your extra credit assignments deadlines are coming up April 1st, and it's not a joke. You'll get extra credit. And they're relatively easy, as I said, but write something good. Let me put it that way. Okay, so today we're going to go deeper into microarchitecture. Remember that we've covered instruction set architectures and you're doing assembly programming. How many people watched the premiere of assembly programming lecture yesterday? Okay, that's good, some people. I'd recommend watching it because that's going to be useful in your labs. We've been talking about ISA, how the hardware gets exposed to the programmer and the hardware-software contract. And we've also been talking about implementing the ISA in these lectures. We're not ignoring the microarchitecture. But today, we're going to go deeper into microarchitecture, talk about principles, fundamentals, and actually create a microarchitecture design from scratch today. Remember, the microarchitecture we looked at in the past lectures, we didn't create it from scratch. It was given to us. And I'm going to ask you to forget about it today because we're going to build up to it again. Okay, and then next week, I don't know if we will get to MultiCycle microarchitecture today, but hopefully we will. If not, we'll start next week. And then after this, it's going to be a lot of microarchitecture to build up to what existing processors do, which is out-of-order execution, and of course, pipelining. Okay, this is the lecture. If you haven't watched it, I'd recommend watching it. Again, you can watch an earlier version of it also from last year because it's essentially the same. Readings, okay, there's more readings to do. These readings are going to get scarce and scarce because your books, unfortunately, don't cover these, let's say, state-of-the-art topics in that much detail. So I actually, I'm going to follow another book that's recommended. I hope it's in the list. Actually, you will add it if it's not. I don't remember. But you don't need to look at it because your book covers it in a different way, as you will see. Okay, this is one of the slides. Maybe this may be the last slide we stopped at. But remember the gas pedal? That gas pedal is the instruction set architecture. That's the interface between the software and the hardware. And that gas pedal, there's something that it promises, right? If you push it, the car will accelerate. If you don't push it, the car will not accelerate. That's all it promises to you. That's the semantics of the gas pedal operation. That's your instruction, right? And but this says nothing about internally how the car is implemented, how that acceleration is implemented, right? And this is a very good analogy of the difference between ISA and microarchitecture as well as we discussed, right? So you can think of the gas pedal as an add instruction. An add instruction is the interface. It specifies semantically that two registers need to be added to each other, and the destination register should get the value of the addition, result of the addition. It says nothing about underlying implementation, as we discussed. There could be many underlying implementations. And that gas pedal is exactly the reason why it's very difficult to change the instruction set architecture. It's very difficult to say, oh, I'm going to now get rid of the gas pedal. What do you replace it with? People are used to gas pedal, right? Okay, if you replace it with something else, then people need to get used to something else. And we discussed that maybe you redefine the gas pedal such that when you pull, it accelerates, and when you push, it doesn't accelerate. Now, if you do that sort of thing, you're messing with the conventions that people have been used to, the programming, let's say. They've developed lots of programs and they need to reprogram themselves. So I think this gas pedal is a really great analogy for this purpose. Okay, So basically, microarchitecture is an implementation of the ISA under specific design constraints and goals. It's not any implementation of ISA qualifies, of course, but our goal is to really satisfy some design constraints and goals. And we're going to get back to those design constraints and goals. Or you can think of this as anything that in hardware without exposure to software. If the programmer doesn't need to know about it, that's microarchitecture, basically. So there are many, many things we will see in this course. Some things we will not see also. Pipelining we will see, for example, in order versus out of order execution. How do memory requests get scheduled? Speculative execution, we will see these concepts. Actually, we'll see a lot of these concepts. I'm not going to talk about these right now. But these are normally part of microarchitecture. They don't get exposed to the programmer. Of course, there's nothing. Let's say this is not set in stone, right? This is a contract, as I said. Somebody can write the contract saying that programmer knows about the voltage and frequency scaling that's going on in the machine. Basically, current machines automatically change the frequency, right? Without programmer's aid. In some machines, you can actually have a programmer dictate when this could be done. So if it's visible in the program, if it's specified in this 5,000-page document, then it is part of the ISA, right? So there's nothing set in stone. That's why I think ChatGPT may not do very well in these things, because there are some architectures that actually expose some of these things to the programmer. Okay, but let's take a look at, let's have some fun. I'm going to ask you whether the following things that are going to be on this slide are a property of the ISA or the microarchitecture, at least in the general case. Add instructions opcode. Who says ISA? Don't be shy. Okay, who says microarchitecture? Okay, you lose if you say microarchitecture because opcode is exposed to the programmer, right? This is defined in that document. The opcode programmer needs to know, or some programmer needs to know about it. Basically, if you really want to instruct the machine to do something, assembly programmer or the compiler writer, you need to know about it. Type of adder used in the ALU, whether it's bit serial or ripple carry. Who says it's ISA? Who says it's microarchitecture? Okay, so the majority wins in this case. You could potentially specify it. I mean, you can have an instruction that says ripple carry add, right? Or you can have an instruction that says bit serial add, right? You could expose it, but this is not done. In no machine that I know of, this is done today. Okay, number of general purpose registers. Who said this is ISA? Okay, coming. Who says this is microarchitecture? Okay, if you're consistently wrong, you can flip your bit and you'll be right. So this is also ISA, right? Because again, when you write a program, you need to specify the register ID, and you need to know the number of general purpose registers. In fact, in the document, in the ISA document, it clearly specifies MIPS has 32 general purpose registers. Okay. How about number of cycles to execute the multiply instruction if you have a multiply instruction? Who says this is ISA? No one. Okay, I think you're getting the gist of it now. Who says this is microarchitecture? Okay, microarchitecture wins, except if the ISA requires you to know this. And there are some ISAs where actually, in order to write code correctly, you need to know the latency of a multiply instruction. We're going to talk about very long instruction word architectures later on in one of the later lectures, and you will see that without knowing this information, that machine will not work. So in dominant architectures today, this information is not part of the ISA. Okay, number of ports to the register file. How many, let's say, read ports versus write ports do you need to have into this register file? Who says this is ISA? Okay, who says microarchitecture? Okay, again, microarchitecture wins here because, again, this is an implementation thing, right? The register file is an architectural concept, yes, ISA concept, but how do you access it as implementation? Architectural concept just specifies what you do to the registers. It doesn't specify how you should do it. You can read the registers serially. You can have 10,000 ports to the register file and use one of them, right? Or you can have only one port to the register file and you read the register file multiple times to get multiple values, right? Okay, let's do one more. I mean, you don't know what pipeline instruction execution is, but you can maybe guess. Maybe it's like assembly line. We're going to talk about it next week. Who says this is part of the instruction set architecture? Who says it's part of the ISA? Oh, sorry, the microarchitecture. I thought that was not a trick question. Okay, microarchitecture again wins. Okay, again, unless the pipeline is exposed in this contract, but usually not. Okay, I guess we have one more. Who says this is part of the ISA, program counter? Okay, who says this is part of the microarchitecture? Okay, here the minority wins. Program counter is part of the ISA because there are instructions in the ISA that operate on the program counter, right? In fact, every instruction operates on the program counter. PC equals PC plus 4 in MIPS, in every instruction's definition, right? If that's specified there, program counter is part of the ISA. And not only that, program counter is actually very widely used in many ISAs, well, von Neumann ISAs, let's say, because you can change the control flow, and the control flow changes the program counter. That's a register that you can manipulate directly, actually. And also, you need to know the value of the program counter so that you can do a PC relative addressing that we discussed yesterday. Okay, so basically, remember, microarchitecture is the implementation of the ISA under specific design constraints and goals, and ISA is the contract between hardware and software. So you will have questions like this in the exam. This is one of the questions that we have on the exam actually consistently, let's say. Okay, so what's a design point? I mentioned this design point. We talked about this actually in the first lecture, but this is really, why are you designing a computing system? It's a set of design considerations and their importance or relative importance. And this leads to trade-offs in both ISA and microarchitecture, essentially. So there are many considerations. Again, I'm not going to talk about every single one of them. These are also, you can also think of these as metrics: cost, performance, power consumption, energy consumption, and many, many other things, time to market, security, safety, predictability, and you can probably add to these. And these considerations are really determined by why you're designing the computing system. Right? What is the problem you're trying to solve? Remember the first lecture, why are we designing why are we designing computers? To solve problems, right? And we want to solve some problems, but different computers solve different problems, right? What is the application space? What is the intended user or the market of this thing? And then you come up with basically considerations. But of course, these considerations are not just related to this part, but also it depends on, for example, how much cost you can tolerate, et cetera, right? And also technology, right? Because there's some technological limit in terms of how much power you can supply to a particular machine. Okay, so hopefully that's clear. So application space is actually quite broad. This is an old paper that actually a beautiful, insightful paper that talks about how microprocessors have evolved over time. And clearly, there are many, many different applications. This paper lists a lot of applications here, which I will not talk about. There are also random software packages, as you can see. But today, there are many, many other workloads also that are not, let's say, explicitly discussed by this paper, like genome analysis, machine learning, robotics, graph analytics, web search. You could keep adding to it, basically. Basically, as we just said multiple times in this course, the application space continues to evolve, and human creativity is not going to end anytime soon, in my opinion. So, okay. But these essentially application space combined with the other consideration, technology considerations, lead to trade-offs. That's the design point, essentially. That's what is meant by design point. Design point is actually application space technology. Why are you designing the computer for? And these lead to ISA level trade-offs, microarchitecture level trade-offs, and system and task level trade-offs. For example, we discussed specialized machines for accelerating machine learning, right? That if you decide to do a specialized machine for accelerating machine learning, you're basically deciding those trade-offs. What is your ISA? You're basically deciding that. Is it general purpose? Probably not in that particular case. What is your microarchitecture? What is the best fit microarchitecture to speed up matrix vector multiplications, for example, right? How do you design the system? How do you get data in and out of this processing unit very fast? And task, how do you design the program itself? Because you're really designing an entire system to accelerate a particular, let's say, class of applications. And you really need to make all of these trade-offs appropriately in order to be successful. Again, we've seen some of these trade-offs, right, at the ISA level. We're going to talk a lot more about microarchitecture level trade-offs going into the future. And clearly, there are system and task level trade-offs as well. How do you divide the labor between hardware and software? We discussed this actually when we talked about ISA, right? Remember the semantic gap example? You have the high-level language at the top, control signals at the bottom. You draw a line in terms of where your ISA is, and that determines what is the effort you put in the hardware versus software. But then you can change that by adding another, let's say, implementation ISA, and you convert the programmer exposed ISA to that implementation ISA using hardware or software translation methods. So basically, these trade-offs can change depending on how you look at the entire system. So it's basically very rich and broad, as you can see. And computer architecture is really the science and art of making the appropriate trade-offs to meet a design point in the end. So I said art here, which is blasphemy in the scientific world, right? How can we do art? Well, every engineer is doing art. There's no way you can just do science, unfortunately, because you cannot model everything perfectly. And the systems are way too complex to do that, at least today. Basically, we do not fully know the future, right? We're designing something today, and that thing is going to be used, I don't know, maybe 10 years later, right? There are people who are still using 20-year-old computers, or older, actually. So how can you actually make this a science completely? You cannot. Impossible today. So basically, you need. That's where the artistic intuition of an architect really comes in. So you do not fully know how the applications will change because new demands may change, right, from the top. There could be some other applications that can make your decisions useless, and the system you designed today for application A may be useless for your application B that the users are running 10 years down the road, or even 2 years down the road. Right. There could be new issues and capabilities at the bottom. There could be some technological advance that will change the trade-offs significantly, such that the design decision you make today is not very useful 2 years down the road again. And then there could be different users using computers in different ways, right? And they may have different demands, and they can actually change what they need. They can change the problem space, basically. And so basically, a lot of things can change. So future is not constant. It also changes, evolves. That's why you really need to make decisions that are not fully based on science. And that's, I believe, the beauty of classes like this that help you make trade-offs across different design decisions, right? In the end, you may not be able to evaluate every single design decision you make. That's also difficult. Well, even if you know the future completely, you may not have infinite time to evaluate these decisions because there's a time to market, right? If you actually wait for 20 years to design your next computer, good luck, right? There have been some companies who have been waiting for years and years to release their next computer. And I think they've been getting behind in the leadership position. You can guess who they may be. I'll leave that to you as a quiz question. Okay, it's a major company. Okay, so basically things change at the top, at the bottom, and users, and that's very hard to predict. I like this analog for macroarchitecture. Before we jump into microarchitecture, I think we should not forget that macroarchitecture is similar. Basically, things that are designed for one purpose may be repurposed for other reasons. Does anybody know the answer to this question? No, there's one in Zurich at least. There are many examples, of course, but this place was designed as a brewery in the late 1880s. And then it was converted to a mill and a cold store. And today it's nothing like a brewery if you go there. There's another example from Zurich. Does anybody know where this is? Somebody guessing. That's not an exam question. Yeah, it's a coffee shop. As you can see, it's nice. But then it's a kind of an artistic coffee shop also, but it used to be electric works, as you can see. And then there's one of my favorite examples from Pittsburgh. This was designed as a church, but now it's a brewery, as you can see, and a place to eat. So things change, as you can see. That's true for microarchitecture as well. Okay, any questions on this? Now we're going to jump into microarchitecture in more detail. I could keep going with those examples, but then we'll never end these examples. Okay, so we know what an ISA is right now. How do we implement it? Basically, how do we design a system that obeys the hardware-software interface? And as I said, I'm talking about a system, right? System can be solely hardware or a combination of hardware and software. Remember that what we discussed, the translation of ISAs. You can actually, ISA doesn't directly have to be implemented in hardware. ISA can be implemented partially in software and partially in hardware. But because of this reason that we discussed. But we will assume complete the hardware implementation for most of these lectures, definitely today and next week, and then the next week. Okay, so basically, the question we're really asking is how does a machine really process instruction, and what does processing an instruction mean? And we're going to assume the von Neumann model for now as well. So what does processing an instruction mean? An instruction is a transformer, basically. It transforms a given architectural state to another architectural state. So there's some architectural, programmable visible state that exists before an instruction is processed. And then you process the instruction, and that produces architectural state prime, meaning architectural or programmable visible state after the instruction is processed. And clearly, this transformation of architectural state into architectural state prime should obey the semantics of the instruction set architecture. Right? That's what instruction set architecture is. We've discussed that. Okay. Now, this looks awfully like a state machine, as we will see. You're transforming one state to another state, and the process instruction can happen in one cycle or multiple cycles. So von Neumann model, just recall that. We have sequential instruction processing. That's what we're going to assume. And we're going to assume a thing like this. And this is what we mean by programmable visible state, if you forgot. Memory, registers, program counter. These are programmable visible. Well, there could be programmer invisible registers also, as we discussed, and we're going to introduce them as we go along in this lecture. And those will be called microarchitectural registers. They will aid the processing that we do to get benefits. Okay, basically instructions and programs specify how to transform the values of programmable visible state. So let's take a look at this in a little bit more detail. As we said, ISA specifies abstractly what architectural state prime should be given an instruction and architectural state. In essence, it really defines an abstract finite state machine, where state is the programmable visible state, and next state logic is the instruction execution specification. So if you've seen finite state machines, you need state and the next state logic, right? So from the ISA point of view, there are no intermediate states between architectural state and architectural state prime during an instruction execution. That's what the programmer sees. Underlying, you can do it something very different. So basically, from the ISA point of view, there's one state transition per instruction. On the other hand, microarchitecture implements how AS is transformed to AS prime. And there are many, many choices in the implementation. For example, we can have programmer invisible states to optimize the speed of instruction execution, multiple state transitions per instruction. That's what we have seen in the microarchitecture that we studied earlier, yesterday and the previous week. Remember the finite state machine? I'm going to show that again at some point today. We do multiple state transitions per instruction. But you don't have to do that. You have a choice as a microarchitect. You could do this. You could transform architectural state to architectural state prime, given the specification of the instruction, in a single clock cycle. We're going to see that this is a bad idea, but we're going to build this machine first. Just because it's simple to build, and also see the trade-offs and see why it's a bad idea. So choice 2 does this basically, transforms architectural state to architectural state prime, but it takes its time in doing so. First, in one clock cycle, it goes from architectural state to architectural state plus some microarchitectural state 1. So there are some other registers that it changes. In the next clock cycle, it goes from, it changes some more microarchitectural state. And the next clock cycle, it changes some more microarchitectural state. And eventually, at the end of the execution of the instruction, it updates the architectural state. So you can see that the intermediate states, intermediate clock cycles are not exposed to the architectural state, because architectural state can be inspected by the programmer or the system. And if you expose these intermediate states, then you're not obeying the ISA. You're basically doing something that is out of specification, that's not expected. Right? So that's why AS stays constant in those transformations in different clock cycles until the instruction is supposed to have ended. Makes sense, right? So this is the second one is called a multi-cycle architecture, and we will see that after you finish the single cycle design. So what we have seen so far was a multi-cycle design. It was actually a good design. That's why we started with that. So basically, given what we know so far, a very basic instruction processing engine can be designed to take only a single clock cycle to execute every instruction. And you can only use combinational logic to implement instruction execution. Sequential logic is the architectural state. Combinational logic specifies basically enables the execution of all of the instructions in the ISA. So there are no intermediate programmer invisible state updates. So this is what we're going to do. Take AS, I'll call it AS from now on since architectural state is a mouthful. You process the instruction in one clock cycle. This is the clock cycle of the machine, the sequential logic. And you produce architectural state prime that's visible to the programmer again at the end of that clock cycle. So you can see this single cycle machine or you can make it pictorial like this, right? And this is very similar to what we have looked at, our finite state machine, right? You have sequential logic, which stores a state and which stores the architectural state, AS. And then there's some combination logic that implements the instruction. And in a single cycle, it produces architectural state prime. And at the rising edge of the clock, it basically latches, it sets architectural state to architectural state prime. So, of course, an obvious question here is, what is the clock cycle time determined by here? Any takers? Nobody? Yes, go ahead. Exactly. Basically, the critical path of the combinational logic plus the sequential overhead, right? So what is that determined by? At a higher level. Yes? That's true, but what is that determined by? Okay, you go ahead. You can say it that way, yes, but I would rephrase it. I think you're going to the right direction as the longest instruction to execute, basically. Basically, the longest instruction to execute determines their clock cycle time over here. Basically, the answer to the first time is critical path, as you guys have guessed. And what's the critical path, longest delay path of the combination logic determined by? It really depends on the longest instruction. And we will see that. And we will see that this is insurmountable because your architecture may be very complex, for example. It may have a complex instruction that may take, I don't know, millions of nanoseconds to execute. And you don't want your clock cycle to be millions of nanoseconds. And we will see that. We will get back to it. But we're going to try to build this machine first. But before we start to build that machine, let's talk about the trade-offs a little bit. So in single cycle machines that we're going to build first, each instruction takes a single clock cycle. All state updates are made at the end of an instruction's execution. The big disadvantage is what I just said. The slowest instruction determines the cycle time, so you have a long clock cycle time. That's why people have designed multi-cycle machines. That's why the machine that we looked at last week or yesterday was a multi-cycle. It was actually beautiful. These machines break the instruction processing into multiple cycles, as well as stages, multiple clock cycles. And state updates can be made during an instruction's execution, except not the architectural state. This is microarchitectural state. This just says that basically architectural state updates made at the end of an instruction execution. And the big advantage over the single cycle will be basically the slowest instruction doesn't determine the cycle time anymore. Slowest stage determines the cycle time. Basically, it's up to the microarchitect to decide what that slowest stage is, because you can chop up the instruction execution in a way you like, such that you can maximize your clock frequency, for example. Because an instruction, maybe an instruction requires a long time to execute given a combination logic, but you say, I'm going to break up that thing to 1 million clock cycles, right? And now your clock cycle length could be 1 nanosecond as opposed to 1 million nanoseconds. And we will see that. But what we will not violate, at least in the design of these two machines that we're going to see, is both single cycle and multi-cycle machines literally follow the von Neumann model at the microarchitecture level. So we're not going to violate the von Neumann model even at the microarchitecture level. We're going to violate that next week when we introduce pipelining, because we're going to start executing the next instruction before we finish the previous instruction. And that's clearly a violation of the von Neumann model, right? Von Neumann model says you go to the next instruction only after you finish the current instruction. Okay, so now let's see how we are going to build this single cycle microarchitecture. So we already know this actually. Instructions are processed under the direction of a control unit step by step. That's, again, core of von Neumann. Instruction cycle is a sequence of steps to process an instruction. Fundamentally, there are 6 steps, as we have discussed. And we know that not all instructions require all 6 steps. So these are the 6 steps that we have seen. So unfortunately, this is also called a cycle, but it has nothing to do with clock cycle as we discussed, right? This is the instruction processing cycle. So in a single cycle machine, all 6 phases of the instruction processing cycle take a single machine clock cycle to complete. That's what we're saying basically. Whereas in a multi-cycle machine, all 6 phases can take multiple machine clock cycles to complete. In fact, each phase itself can take multiple clock cycles to complete. If you remember the fetch stage, fetch phase in the LC3 microarchitecture we studied, it took at least 3 cycles, right? If you remember stage 1, 2, 3 over there. We'll get back to that. Okay, so if you view instruction processing another way, basically the transformation of the architectural state or some data to data prime, architectural state prime, is done by functional units. These are the units that operate on the data. And these units need to be told what to do to the data. So based on this observation, we normally divide an instruction processing engine into 2 components, which is data path and control, essentially. And data path consists of the hardware elements that deal with and transform the data signals. And ALU is one example. Register file is another example. Right? So there are many things, basically. They consist of functional units, ALU is an example, that operate on the data, storage units that store data like registers and memory, and then hardware structures that enable the flow of data into the functional units and registers, wires, muxes, multiplexers, decoders, tri-state buffers, etc. And we've seen all of these also in the LC3 data path, right? So data path is distinguished from control logic. Oh, I'm going to get back to that. So control logic consists of hardware elements that determine control signals, and these signals specify what the data path elements should do to the data, right? They basically dictate the flow of data in the machine, right? And control logic is necessary to ensure that the flow of data is correct according to the specification of the ISA. So always remember that there's data path and control logic, and you can design these separately. And we will see that in the SingleCycle microarchitecture we design. We're going to design the data path first. We're going to show the control signals, of course, because data path without any control is kind of meaningless. So we're going to add control signals, but then we're not going to design the control logic until we finish the data path. And then after that, we're going to see how we design the control logic. In the SingleCycle, it's going to be very simple, actually. Once we go to multi-cycle, control logic complexity increases. And control logic complexity will increase as we keep going in the lectures. Okay, is this distinction clear? Data path, control logic? Okay. Okay, and you've seen this, as I said, right? You can see over here that, and we clearly distinguish the signals. For example, this is a control signal. Control signal is white arrow. Data signals are black arrows, right? So control signals are controlling what this mux does, whether this program counter should be loaded in this cycle or not, whether the instruction register should be loaded in the cycle or not, whether this tri-state buffer should be enabled in the cycle or not. Basically, you can see a lot of control signals, right? Whereas data path elements are ALU, multiplexer is a data path element, but it has a control signal that dictates what it needs to, how the data should flow through the multiplexer, right? And register file is also a data path element, but it has some control signals that dictate what registers should be written and if they should be written, right? Or read. So basically, we've already seen control signals and data path, and we kind of distinguish them also. Okay. So let's take a look at how control and data is done in a single cycle versus multi-cycle machine, because this is important. So in a single cycle machine, you don't have time. You have to do everything in one clock cycle, everything specified by an instruction. That includes data flow as well as control. Meaning, you need to generate the control signals in the same clock cycle as the one during which data signals are operated on, right? This is fundamentally slow in the sense that you have to decode the instruction and then operate on the instruction, right? Basically, everything related to an instruction happens in one clock cycle. As a result, you need to process, you need to serialize the processing. On the other hand, in a multi-cycle machine, you have some more room. Control signals that you need in the next clock cycle can be generated in the current clock cycle, right? While you're doing data path processing with some control signals right now, you're generating the control signals for the next clock cycle. So you can overlap data and control processing in a much better way this way, as I already say over here. So that you get more parallels. And you will see this more when we actually design the machine. You kind of seen it earlier when we discussed, but I didn't explicitly point this out. So if you really want to see a very nice multi-cycle machine, your book, Pat and Patel book, Appendix C, has a microprogrammed multi-cycle microarchitecture that I would strongly recommend. It's a beautiful microarchitecture. We're not going to, unfortunately, study it. I have backup slides on it, but we don't have time to study it. We'll study some other type of multi-cycle microarchitecture, hopefully today or tomorrow. We'll see. Well, tomorrow, not tomorrow, next week. Unless you're willing to come here tomorrow and we can have a lecture. Okay. Okay, so there are many ways to actually design the data path and the control. We're going to see some ways, not all of the ways, but just to give you the critical thinking, what we're going to design is not the only way. There are actually many, many ways, and you have a lot of flexibility. It's always a trade-off, basically. For example, data path and control can be done in single cycle, multi-cycle, or pipelined, or out-of-order execution, as we will see. There could be a single bus, like we have seen, right? There was a single bus in the LC3 microarchitecture, or there could be multiple buses. Actually, what we're going to see in the single cycle is going to be, in single cycle microarchitecture is going to be multiple buses. We're going to not use a single bus. Your control logic could be hardwired, combinational, or micro-coded, micro-programmed, sequential control, as we will see later. Basically, this says, how do you generate the control signals? Do you use just combinational logic, or do you store the control signals in a memory structure? And both ways are done in existing systems, actually. In cutting-edge machines, some control signals are generated using hardwired combinational logic, but some of them are stored in memory structures because there are just a lot of control signals that you need, and it's easier to do that. But what's important to know is that control signals and the structure of the control signals depend on the data path design. That's why we're going to design the data path first, because data path is really what are you going to do with this instruction, right? How are you going to add two values? Where do those values come from? Memory, how do you determine the address? These are actually data flow issues. Control basically orchestrates when do you do what and how the data flows between the elements. So control signals are very much dependent on the data path structure. That's why you start with the data path design normally. Of course, you can iterate both of them later on. Okay, any questions? I'm still giving you an introduction, high-level introduction. We have not jumped into the design yet. But before we jump into design, I will also flash forward some performance analysis. We're going to do more performance analysis in this course. And this is performance analysis in the sense that it's performance, execution time. You could also do power, energy analysis, which is also important, but we're not going to do that now. So execution time of a single instruction. And when you do performance analysis, it's always important to know the execution time of a single instruction. And we normally specify this as how many cycles does it take to execute this instruction? This is called CPI, cycles per instruction, times the clock cycle time. What is the clock cycle time? Hopefully it's obvious, right? You have a clock cycle time for your machine that you determine based on your critical path and the design. And if an instruction takes n cycles, you multiply that clock cycle time by n. Okay, so that's a single instruction. What about an entire program? Basically, it's really summing up over all instructions in the program, this value that we just compute for a given instruction. You compute it for every instruction and you sum them up, assuming instructions are processed sequentially, obeying the von Neumann model completely. Right? We're going to break that later on. But this is what we're assuming right now. So this can also be expressed as number of instructions times the average cycles per instruction across all of those instructions in the program times the clock cycle time. So these two things are equivalent, assuming you average the CPI correctly across the number of instructions. And this is a performance equation, basically, execution time of a program. And you can see that you have actually different levers over here. You can change the number of instructions to do the same work. That requires changing your program or how it's compiled, or changing a different ISA. You can design a microarchitecture where clock cycle time is high, or clock cycle time is low. Or you can design a microarchitecture where the average CPI is low. Or you can try to do all of them as low as possible, right? So there are actually, there are 3 degrees of freedom over here. They're not completely independent of each other, unfortunately, as we will see many times later on. In fact, whenever you try to reduce the clock cycle time, almost always you're going to increase the cycles per instruction, as we will see just now in this bottom part. Okay, does this make sense? So we're going to assume that number of instructions is constant for now. We're not going to change that. Let's take a look at single cycle microarchitecture performance. And then multi-cycle. So single cycle means obviously CPI is 1, right? For every single instruction, cycles per instruction is 1. That's by definition. And we just discussed earlier that the clock cycle time is long. Actually, it should be long, not long. And we will see that empirically later on. But take my word for it for now. I think you can reason about it also. So basically, you don't have any freedom over here, right? The only freedom you have is changing the clock cycle time, assuming number of instructions is constant, as I said, right? You have somebody designed the compiler for you, assume that for now. So you can only try to change the clock cycle time. Whereas multi-cycle microarchitecture, by definition, makes CPI dependent on the instruction. Cycles per instruction is different for each instruction. And hopefully you can make the clock cycle time short, right? And that's the purpose, right? You make the clock cycle time short and have different instructions take different number of cycles to finish. And hopefully the designer can make sure average CPI is small, let's say. It's not going to be 1, clearly, because that's single cycle at that point. But you could try to get as close as possible to 1, right? Hopefully small. And this really depends on the implementation. How do you actually execute the instructions? What is your instruction mix? Do you actually execute very complicated instructions that take thousands of cycles? Or do you execute instructions that take only 1 cycle usually? Depends on the program also, right? As you can see. But we assume that number of instructions is constant. But basically, this enables trade-offs right now, right? In multi-cycle microarchitectures, you have 2 degrees of freedom to optimize independently, assuming instructions is constant. Really, you have 3 degrees of freedom, like we see in the above. Okay. So that's why we're going to look at single-cycle microarchitecture, and we're going to dismiss it quickly. I'm not suggesting that we're going to look at it quickly because I want to go through the design fully. Okay, any questions? So now we can jump into the ground-up design of a single-cycle microarchitecture. Okay, remember, this is our single-cycle machine, and we're going to implement it just like it's shown over here. And we're going to start with the state elements, and I'm going to use something from this other book. It's Patterson and Hennessy, but it's very similar to your book. I just like giving you different examples just to show that these things are very similar across the board. And we're going to look at MIPS in this case. So basically, these are our state elements in MIPS. These are our architectural state elements. We have a program counter. And you can see that there's a no load program counter. Forget about what you have seen with microarchitecture with LC3 right now. We're going to start from a clean slate and design a MIPS microarchitecture in a single cycle. What you've seen was multi-cycle. Forget about it. This is a single cycle. So we're not, basically, the assumption is that every clock cycle, the state gets updated, right? So program counter gets updated every clock cycle because you go to a different instruction, right? So there's no need for a write enable signal for this program counter, right? Okay, we're going to divide memory into 2, unfortunately, instruction and data, just to make things simpler. We don't have to do that exactly, but we're going to try to make this thing simpler. So we're going to supply an instruction address, and we're going to get the instruction, and we're going to assume this is combinational. Basically, you're not going to wait. Well, it's going to take some time, but we're going to assume that it's all combinational. This is the other memory, data memory. Here, we're going to supply an address, and the address will give us data, assuming the mem read signal is asserted. If the mem write signal is asserted, we're going to supply address and data, and the data will be written to that location specified by the address. And you're not going to get a read data at the end. And this is the register file. We have 2 register file ports for reads. You can see that there are 32 registers. And we have 1 port for write, and then the write data over here. So you can use 2 different IDs or the same ID to read 2 different registers or same register, let's say, from 2 different ports over here. And you can use the write data as well as the write register ID to write data to 1 register. So this is all combinational also. You can do it all at the same time in a single clock cycle. Makes sense, right? And you know how to design these things right now. Yes? Yeah, basically it's for instructional purposes. We're not really splitting up. Yeah, that's a good question, basically. Underlying, we're not fully von Neumann, but there's no real reason to do it. You can actually design a single memory, except it just complicates how we look at the system. You need to add more ports, basically. Does that make sense? You need to add basically an instruction. Basically, you need to make it look like the register file. It just makes the figures much uglier, let's say. That's why I said this is really von Neumann, but we're breaking it up just for instructional purposes. But that's a very good question. Okay, so your book, which you're going to read on your own, hopefully, has something similar, basically. As you can see, it also has instruction memory and data memory, very similar. It just uses some different terminology. Program counter, prime program, this program counter, sorry, this is the register file. Again, I'll let you read your book, but what I'm going to go through is essentially what your book will do. Let me see if there's anything that I need to talk about. I think we talked about these things. I'm going to talk about memory a little bit. Yeah, I'll let you read the book over here. But let me talk about memory. We're going to assume ultra-fast memory and register file. We're going to assume combinational read, meaning the output of the read data port is a combinational function of the memory contents and the corresponding input address. It's very similar to what we have seen, actually. The memory we have seen earlier was like this. We're going to assume synchronous writes, meaning the target location is updated at the positive edge clock transition when write enable is asserted. And again, this is what we have seen in sequential logic, right? Memory gets updated at the positive edge of the clock, which means that you cannot affect read output in between positive clock edges. So you have the full clock cycle to actually use the output coming from the memory. Okay. So there's single cycle synchronous memory. That's what we're going to assume. Or it will take some time, but it may not occupy the entire cycle. Basically, the key difference is contrast this with memory that tells when the data is ready. So we're not going to use that ready signal. We're not going to have that ready signal. We're going to get back to this later on. So if you didn't understand this part, don't worry about it. But basically, the memory will be seamless. You give it some address, it'll provide you the data. In real life, it's not that seamless, as we will see later on when we discuss memory. Okay, so basically, I'm going to follow this Patterson and Hennessy book, which divides and your book also divides the processing into 5 generic steps. You have instruction fetch, basically program counter. This is the data path, basically. We're going to see this data path. We're going to start with this data path. To be able to fetch instructions, you need to connect the program counter to the address port of the instruction memory, and then get the instruction out. And then in order to be able to decode the instruction and do the register operand fetch at the same time, we basically supply some of the instruction bits to the source register IDs and some of the instruction bits to the destination register ID. And then we read the registers, as you can see over here. And then there's something else coming from the instruction going into the ALU. That's going to be the immediate, as we will see. And then to process the instruction, we have the ALU, which gets connected to the data output ports of the register file, as well as the immediate coming from the instruction, sign extended, etc. And then that ALU will do the execute or address generation, depending on the instruction, of course. And this ALU will provide the address to the data memory, assuming this is a memory operation, and we will get the data out from the data port. And then there will be a store write back result. Depending on the instruction, the result may be coming from the memory and being written to the register file with the port specified by the instruction. And also there's a control signal that's not shown over here clearly, right? So this is the data path, only the data path. There are no control signals over here. Or the data that's to be written or stored into the register can be coming from the ALU, depending on the instruction. And the destination register is specified by the instruction. So that's all you need to execute instructions, actually, as you can see. Make sense? So this is our data path. This doesn't show any control signals over here. Now we're going to make it a little bit more complicated. And also see how we implement instructions on this data path. So you can actually see the different stages over here. We're going to later pipeline this, but let's not get ahead of ourselves. Okay. So basically, you need to, in order to design a microarchitecture, you need to provide the data path and control logic to execute all ISA instructions. So what is to come? We're going to build up to this, basically. It looks complicated, but it's really not complicated. And this is the other complete single cycle processor from your book. So we're going to start with a single cycle data path for arithmetic and logical instructions. So let's start, and then we're going to take a break. So let's start with a simple instruction. This is an R-type ALU instruction. You've seen this already, right? You've seen what it does. It's a register to register add. There's a specification of it, as you can see. And the specification says, if the memory pointed to by the program counter has this encoding, that's R-type, then the general purpose register RD should get the value of general purpose register RS plus general purpose register RT. Okay, and PC should be incremented by 4. Makes sense, right? We know this. So this is our data path. Our data path actually can do this, except we need some control signals. So we have this program counter. So let's handle the PC first. You need to basically provide the data path elements as well as the control logic to execute this instruction. So the data path element, PC, we want the PC to be incremented. So let's have an adder, specialized adder that increments the PC by 4. Okay. And at the end of the clock cycle, PC plus 4 gets stored into PC because you write to PC every clock cycle. And then we also take the PC to read the instruction memory, get the instruction out, and instruction bits now specify which register we're going to read. This is the destination register, or this is the read register, sorry. This is the first source, second source, and the destination register. Okay, now we index the register file, get the data out, the data path. This is how the data is flowing right now, nicely. We didn't need any control signal so far. Well, so far, we're going to need soon. And then we basically got the data out in this data path, and now there's an ALU. The question is, what should the ALU do? Well, there needs to be a control signal that's controlled appropriately. And so we need to generate a control signal that says ALU should do add. We'll see how it's generated, but you will see that later. Basically, this control signal should be set to add, and then the ALU provides the result, and that gets connected to the right data port. And you already have the right data register ID from the instruction bytes over here. And we need to set a control signal saying that we should write to the register, right? Because we don't want to write to the register if the instruction is not going to write to the register. Okay, that's the write enable signal for the register file, basically. And this is it. This is all you need if you were executing only add instructions that are registered to register. Beautiful, right? So we started with a blank slate. Now we're going to make this more complicated. Well, ALU design, of course, there's some internal ALU, which we're not going to talk about, but you know this from before. So there needs to be this thing needs to be designed, but of course, this thing also needs to be designed, and this thing also needs to be designed, and this thing also needs to be designed. Okay. So okay, we're still talking about arithmetic instructions, but there are other types of arithmetic instructions, I-type arithmetic instructions. Basically, these have 2 register operands and 1 immediate. And the specification is that if the memory pointed to by PC has this sort of encoding, then general purpose register RT should get general purpose register RS plus sign extended immediate coming from the instruction, and PC should be incremented. Okay, so this was our data path with the earlier add. So how do we change this data path so that we can accommodate I-type instructions? That's it. So what have I done over here? Basically, the second input of the ALU should not be a register, right? Because that's what the instruction specifies. The instruction specifies that it should be a sign extend immediate. If it's an I-type ALU, it should be a sign extend immediate. So that means we add a multiplexer. We add a multiplexer saying that if this instruction is I-type, don't select this one. Select whatever we've added over here. Yeah, actually, I kind of lied to you because the sign extended is added for I-type, right? You didn't need it for R-type. Sorry about that. I should have better pictures, but I'm limited by what pictures were supplied earlier. Okay, so basically, you can see that the second source should be selected from the sign extended 16-bit immediate that's coming from the instruction over here. Okay, so this way we enable the data flow correctly into the ALU, and we computed the correct results, source register specified by the instruction, and the immediate, sign extend immediate specified by the instruction again. Now, we also need to play a trick over here, unfortunately, because the register ID that we're going to write to is not coming from the same place in the instruction of the register ID that we were going to write to in an R-type instruction. Basically, if you go back and look over here, the destination register is RT. It's coming from these bits. Whereas if you go to the R-type instruction, destination register was the next 5 bits, if you will, right? So you basically need to have the correct index, and the destination register in this case will be destination specified by the bits 20 through 16, because the bottom bits 15 through 0 are the immediate, right? Because of the specification of the instruction. So basically, to be able to execute I-type instructions on top of R-type, we needed to add this sign extension logic. We need to add this data path wire coming from the instruction, the 16-bit wire, sign extended to 32 bits. We needed to add this multiplexer. We need to add this control signal to control this multiplexer. We needed to add this multiplexer to decide appropriately which destination register needs to be written, and we need to add a control signal to control the multiplexer. And both of these multiplexers are controlled using the same signal, whether the instruction is I-type. So we complicated the data path. We also complicated the data control logic. Well, control logic we are not looking at yet. And of course, register write control signal needs to be set to 1, and ALU operation needs to be set to add. Okay? So now we can execute R-type and I-type ALU instructions. It's very similar for subtraction, for example. You just need to change the ALU operation right now, right? Or NOR. You just need to change the ALU operation. Okay, so we have seen this actually before, right? If you, again, I will not go into LC3 in a lot of detail, but we did essentially the same thing for add with immediate or one literal in LC3. So a lot of the ISAs are very similar. As you can see, you sign extend the bottom, I think 6 bits in this particular case. And you need to have a multiplexer to decide whether the second input of the ALU is coming from a register or a sign extend immediate. And in LC3, bit 5 determined whether it was ALU or sign extend immediate. In MIPS, it's not that easy. We'll see that. Okay, any questions? Okay, I think this is a good time to take a break. Let's be back at 15:20, and we're going to do more of this. We're going to complicate things more. Hopefully in a good way. Okay, let's get started. So now we're going to move on to data movement instructions. But just recall that we designed the data path for R-type and I-type ALU instructions. Now we're going to scrap it and just do data movement. And we're going to look at, actually not scrap it completely, but we're going to try to add data movement on top of it, right? We're going to start with load instruction. And if you remember, load word in MIPS is actually an I-type instruction. If you go back to I-type add over here, it's going to be very similar to this, right? Except instead of add, we'll have the load opcode, and we'll have a base register, and then we still have the offset or immediate. Yeah. So basically, load word is very similar in terms of what it does, except it uses the sign extend offset plus base register's value to compute an address. So it's going to do the same thing I-type instruction is doing, I-type add is doing, right? Remember, I-type add was adding general purpose register base plus offset, sign extend offset. We're going to do the same thing, except we're going to use that address to index into memory and get the data value and place into the destination register specified by RT, which is also specified by the add immediate instruction because it's in the same location. So in that sense, those instructions are going to be very similar. The data path elements are going to be very similar to the I-type instruction. So this was the data path we had earlier, if you remember. I mean, I don't have everything over here because I'm going to connect things, but let's take a look at how we execute load over here. So we have the support for executing I-type instructions. The second operand of the ALU, second input of the ALU can come from a sign extend immediate, and load is I-type. That's good. And then the destination register is coming from these bits 20 through 16 over here. That's if it's I-type, and load is I-type. So this control signal will be set when the load is executing. But now we use the address calculation, which happens as general purpose register read from the first data port plus sign extend immediate coming into the second input of the ALU. And the result needs to get connected to the address port of memory, as you can see. That's what's needed for load. And the data that's read from memory should be connected to the write data port of the register file. Okay, and to be able to read from memory, we should set the mem read signal to 1, and we should set the mem write signal to 0 because we should not be writing to memory clearly, right? Basically, you should not do any harm. If the instruction doesn't specify something that potentially causes harm, don't do it. You should not update memory, basically. Okay, so this is what's needed for load word, as you can see, right? We just minimally extended the I-type data path. Yes. Oh, that's because of MIPS, right? MIPS has byte addressable memory, and each instruction is 4 bytes. So you need to increment the PC by 4. Okay, that was true for all of the instructions, not just this one. That was true before also. Okay, so this is the load word data path. We're going to expand it fully. This is not fully correct if you were following, because how do we actually make sure that both load word operates on it as well as add I operates on it? It doesn't work, right, clearly, because add instruction needs to get the ALU results and write it back to the right data. So we need a MUXL over here, multiplexer, and we're going to add that soon. But we're looking at the load word data path only, as you can see right now. So stored word data path is very similar, actually, as you can see, except we're going to do a store. The address calculation is exactly the same as load word, sign extend offset plus base register. And except we're going to do a store. We're going to take the general purpose register specified by RT and store it into memory specified by address. Okay, so let's take a look at store word only. Ignore the load word earlier. So to be able to store, address calculation is basically general purpose register, the first register over here. Well, Yeah, exactly. And then add it to its sign extended 16-bit offset. That's good. That's our address calculation. Now this address needs to be, the ALU result is it calculates the address. That needs to be connected to the address. That's good. Now what should we do to this port? Now that needs to come from the register file. That's good. So you can see that we're actually making use of what comes out of the register file second port over here, as specified by the store word instruction. Makes sense because that RT is actually, let's go back to this RT. This bits 20 through 16 is also supplied to read register, as you can see over here, and we're reading it, okay? So we're gonna write this data that we read from RT, or register indexed by RT, write this data into address specified by the ALU result. So to be able to do that, we need to set the control signals appropriately. Mem-write signal should be 1, and we should not be reading from memory. I mean, I guess reading from memory doesn't do any harm, but we don't need it. At least it will save energy, right? If you don't. Okay, so basically, this is it. But this is not it, really. You should not be writing to the register file, right? Do no harm. So store word doesn't write to the register file, and we should not be changing the register file contents. So this signal needs to be set to 0. That's the importance of setting the control signals. And this executes a store completely as it's specified by the instruction set architecture. Make sense? So now let's combine these two, load word and store word. So remember, load word was like this. ALU result gets to address, and then we read the data out here. And the control signals are set appropriately. If it's a load, we're actually writing to the register. If it's a load, we're reading from memory, but we're not writing to memory. If it's a store, address is coming from the same place, at least in this addressing mode. Whereas data needs to be connected over here into the data read output port, second read output port of the register file. I need to set the control signals exactly the oppositely compared to the load. Okay, now let's combine these two, load and store. This is what we have right now. So we have the data path components that we added for load and store, as you can see. And we have the read data coming out over here. The control signals now, if it's a load, memory read signal should be set to 1. If it's a store, memory write signal should be set to 1. Oop. And register write signal should be set to 1 if it's not a store. Makes sense, right? So all of the other instructions that we've studied so far are writing to the register file, except stores. Now, this is load store. If you really want to do load, store, and all of the R-type instructions that we studied so far, you need to add this multiplexer also, as we discussed, right? Because load instructions read the data from a memory location and write it to a destination register. But R-type add or I-type add instructions take the ALU result and write it to the same destination register. Well, not the same destination register, depends on the R-type or I-type instruction, basically, but some destination register. So the destination register value, write data value coming into the register file port can come from either here, ALU results, or the output port of the memory, as you can see. So we need a multiplexer to be able to execute both of these types of instructions. And the multiplexer is called the memory to register multiplexer, aptly. And you can see that it's controlled by isLoad, meaning if it's a load, take this, it selects this data input and passes it to the output. If it's not a load, it selects the ALU result and passes it to the output. That makes sense, hopefully. So this is all of the instructions that we've looked at so far can be executed. That's why I call this a non-control flow instructions. Of course, all of the things that we studied, right? If you want to add another instruction, you need to provide the data path elements as well as the control signals to execute it. Does that make sense? Okay. So this is how you build a data path, basically. This is how you execute the instructions. Add data path elements that's needed and the control signals that are needed. And this is one way of building the data path. Okay, any questions so far? Otherwise, I'm going to jump into other things. Oh, okay, I already discussed this, so that's why it's circled. So now let's take a look at control flow. So control flow is going to touch some other parts of the data path without touching, let's say, the back end of the data path. So let's do the simple control flow. This is the jump instruction that we first studied, right? This is a J-type instruction, as you can see. basically the semantics look like this. You'd first calculate a target address, incremented PC, concatenated with 26-bit immediate, concatenated with 2 zeros at the end, because this is byte addressable again. It doesn't make sense to start an instruction at a, let's say, non-aligned address to instructions. We're going to talk about that later on. And then the PC is set to this target address. So there needs to be some target address computation logic, and there needs to be a way of supplying that computed target address to the program counter. In this case, the computation logic is relatively simple. You basically slice bits, right? You take 4 bits from the incremented program counter, you take the 26 bits from the immediate, and then you basically set the bottom bits to 2 bits to 0. So the computation logic is actually very simple, as you can see, right? You're just doing bit slicing. But you need to set it to PC. So basically, this is the data path that we built earlier that can execute non-control flow instructions. Now let's add the jump to it. Let's start with the wrong way of adding it. Basically, the first thing you should do is do no harm in parts that are not involved in jump, right? And clearly, jump doesn't say we're writing to a register. Jump doesn't say we're reading or writing to memory. So we should not write to a register. We should not write to memory. To save energy, we should not read from memory. This multiplexer we don't care about. This ALU operation we don't care about. This other multiplexer that's not shown over here we don't care about, right? So there are don't cares also. Okay, I mean, these don't necessarily need to be don't cares. For example, if you want to save power in your ALU, maybe you disable your ALU with some control signal, right? But we don't have that control signal over here. In modern processors, you can disable structures. For example, you can power gate them or clock gate them such that you don't supply the clock and or even power. So that's possible. That's another control signal, but we're not studying that. So modern processors are more complicated. But basically, at the very basics, you should do no harm. Don't change the architectural states in a way that's not specified by the instruction. That's why these register write and memory write signals are 0. Okay, so a jump is really involved over here, at least this type of jump, because we're going to look at conditional branches later. That's going to involve the ALU. Okay, this is what we do basically. We take some instruction bits coming from the instruction memory. This is the program counter. We read the instruction. We take the bottom 26 bits, concatenate it with the program counter's top 4 bits, and set the bottom 2 bits to zeros, and then supply it to the program counter. Now the program counter needs a multiplexer, because in case of jump, multiplexer selects the output of this concatenator. For all other instructions that we have seen so far, the multiplexer selects PC plus 4, right? All other instructions increment the PC. Multiplexer changes the PC in a different way. This sounds good? Not exactly, because it's not completely correct, and this is a mistake that you may make when you design this. I mean, it's good. It's correct in the, let's say, high-level sense, but it's not correct in the sense that we got the wrong program counter, right? The instructions that specifies, remember this crossover here, it's not the program counter. It's not PC. You should get PC plus 4. That's the specification of the instructions at architecture. If we go back over here, PC is really the incremented PC. So you may get the wrong top 4 bits. So you should really do this one. Get this output, PC plus 4, and concatenate it with the 26 bits coming over here, and you should really not get this PC over here. Make sense? Basically, do what the instruction set tells you to do. That's the moral of it. Makes sense, right? So these mistakes are actually relatively easy to make. This PC plus 4 issue exists in all types of architectures like this, and MIPS actually complicates even more. There's something called delayed branching that we will discuss later on that makes it a mess. And we will see why that's a bad idea later on, but let's hold off on that. So branch logic is actually more complicated than what we're describing over here. Branch or jump. Okay, so that was unconditional jump. There are actually other unconditional jumps that complicate this data path. For example, jump register. Jump register says, take the value of a register specified by a register ID, place it into the program counter, right? Which means you need to provide a data path wire from here to here and complicate this multiplexer, right? Now, that's not just is jump. It depends on the type of the jump, right? The control of that multiplexer. Jump and link says, well, okay. Basically, this is the specification of the jump register. As you can see, we just did that. Jump and link is a little bit more complicated, right? Basically, what you do is you compute the target address just like we did with jump. you set the program counter to the target address, but you also store the program counter +4 incremented program counter in a register specified by the instruction, so that you can return back to that location. This enables a function call, basically. You jump to some location, but you already stored the next instruction just before you jump, the address of the next instruction just before you jumped. So you can do a call, basically jump and link. And then when you do a return or use that register or jump to this register ID over here, you'll go back to where you called from. Okay. So this complicates the pipeline clearly. Let's see what you need over here. So not only that, well, in this particular case, jump and link, the address should be this one. The PC should be updated using the concatenation logic that we discussed. But we also need to provide a path to actually write the program counter +4 into a destination register. And this is also not correct. Basically, you should really write the program counter +4 to the right data. So there's a path from program counter +4 to the right data port. And I'm not going to complete this because now you can see that things are getting complicated. But it's relatively easy. Once you know what the instruction does, you need to basically provide the data path support as well as the control support to do that. So we need to add another mux for jump and link. And then jump and link register does it in a different way, basically. The address calculation, the target address calculation is basically very similar to jump register, except you also need to link it, meaning store PC +4 in a destination register specified by the instruction. So we're not covering these instructions in detail. That's why I didn't do much over here. But there are different types of jumps, as you can see. As I said last time, these are also called call instructions. You're calling. These are there to support function calls, and among other things, other constructs. These are also called indirect branches, by the way. Your branch is indirect, and the address is specified in the register, as you can see over here. These two are indirect branches, actually. This is a little bit different because the PC, the target address is not in a register. Okay, so basically, if you want to design a MIPS processor, you should take the MIPS ISA manual, which is not this one, this is a cheat sheet. The MIPS ISA manual is long. You basically need to provide the support to execute every single instruction, the data path support, the control signals, and then the control logic support. Basically, you need to repeat what we have done for hundreds of instructions and make sure you didn't do anything wrong. Makes sense, right? So this is basically, we start from a blank slate. Now we actually have a processor that can do some things, hopefully. But there are more things that you need to do. Okay, let's look at some of the more things that we need to do. Conditional branches. Clearly, these are a little bit more complicated because they do a lot. I mean, if you just look at the specification of the instruction, it's more complicated, right? So this is branch if equal. There are different variations. Branch if not equal. Branch if one register is less than or equal to 0, or branch if one register is greater than or equal to 0. Okay? So branch equal and branch not equal compare two registers, RS and RT, whereas branch less than or equal to 0 or greater than or equal to 0 test one register. So they're slightly different from each other. Their control logic will be different also. But let's take a look at just branch equal. You can imagine the other things, other variants to be implemented also. So if the instruction is a branch equal, then what do? We first, well, not first. These are all happening in parallel, right? We calculate the target address. The semantics specify that target address should be calculated as incremented PC plus sign extended 16-bit immediate times 4. And we're going to set PC to that target if the source register is equal to the second source register, or RS and RT, right? If both of these registers are equal. Otherwise, we set PC to PC +4. Makes sense, right? So it's a conditional updating of the program counter based on the condition that's computed by a subtraction or equality check. Okay. So let's take a look. I'm not going to completely complete it because this is fun for you to think about it. But basically, we need to provide some data path elements. So ALU, for example, this particular ALU supports subtraction. And if register A is equal to register B, the result of the subtraction should be 0. So you can actually have a subtractor and a 0 checker. Or you could actually do it with, like what we have seen, equality checker, right, in the past. So there could be multiple ways of implementing whether to check whether two values are equal. But basically, we need to set the ALU operation correctly. We're not writing to a register, clearly. Do no harm on the data path portions that are not related to conditional branches. But now we have another adder over here, which is going to calculate the target address as specified by this instruction. PC plus sin extend immediate times 4, left shifted basically. Times 4 is you left shift by 2, right, in binary. So you take the bottom 16 bits, sin extend it. We actually already have this for I-type instructions, that's good. But now we need to add logic to left shift it and add it to PC plus 4, which is coming from here. So again, you need to be careful. You should not take the PC from here. You should really take PC plus 4 according to the specification of the instruction. So it should be connected over here. Okay, so this is our branch target address calculation adder. We need to add a special adder for this, as you can see, right? Why? Because we're using the ALU to do something else, right? Okay, so now we have 3 types of adders in our system. And that's going to be one of the disadvantages of single cycle logic also. MultiCycle can be more frugal in this sense, and we will see that. Okay, so that's going to be input to this increasingly complicated multiplexer in front of the program counter because it needs to support different types of branches. And if the instruction is a branch equal instruction, we need to select this over here. Not quite, because it's a conditional branch, right? So when do you select that? So that's why you need to complete this. But basically, there needs to be some branch control logic, which I will show you later. If the two are equal, if the source and destination are equal, the branch condition will be set to 1, meaning they are equal. Yes, branch should be taken. Only if the branch is determined to be taken, this output of the adder that calculated the branch target address as specified by the BEQ instruction should be propagated into the PC. Otherwise, this multiplexer should select PC plus 4, right? So now we have a control signal that's a little bit different in the sense that just by decoding the instruction, we don't know how to set this control signal, right? Because the control signal is dependent on the processing in the data path because of the specification of the instruction. The instruction says if register 1 is equal to register 2, register source is equal to register T, RS is equal to register T, then TC should be updated with this target address. Otherwise, PC should be updated with PC plus 4. So in some cases, as you can see, the control signals that are needed to correctly execute the instruction will be dependent on the data signals. And this is one of those cases. Branch conditions determined by the 2 data signals and their comparison. Okay? So we're going to see this a little bit more. Okay, that's why conditional branches are actually very interesting. We're going to see conditional branches even more later. It's going to be a lot of fun. Okay, so as I said, MIPS actually is even more complicated than this. Let me give you the basic idea, even though I don't want to spend much time on it. So in MIPS, the semantics of the ISA specifies that the instruction that comes right after the conditional branch is always executed. Basically, you have conditional branch at PC, you have another instruction at PC plus 4, you have to always execute PC, whatever that instruction is that comes after conditional branch. We will see the reason for this later on. But this is the semantics. So it's not as simple as what I just said. You need to remember the target address and get that taken into effect after the next instruction is executed. So things are a bit more complicated. So this is where the semantics of the ISA can make things more complicated. This is a bad idea, delayed branching, as we will see. I normally don't dismiss ideas as a bad idea, but this is a very bad idea. And we will see the reasons of it because it violates something really fundamental, basically. It really ties a particular microarchitecture implementation to the ISA. You should never change the interface, assuming a particular implementation. And that's what these MIPS, original MIPS designers did. Unfortunately, technology evolved as in ways they couldn't have predicted. As a result, the MIPS architectures like MIPS and Spark are, unfortunately, have to implement this delayed branching forever. Because once you have it, you cannot remove it, right? Okay, that's why you need to be careful in designing the ISA. Okay, so basically, this is putting everything all together. And now I actually show you how things are done a little bit more detail. So let's take a look at this a little bit more. So this is the full thing that we kind of built incrementally, but we never showed the full thing over here, right? These are the instructions. But let's take a look at this branch condition logic because we just talked about it. So basically, ALU gets these 2 registers and this multiplexer. So you can see that the orange signals over here are control signals, and there's a control box that determines the control signals. And you can see, basically, a lot of these are intuitive. Regdest is basically, are you writing to the desk? Which ID, which instruction bits are you using to actually decide which register you're writing to? Depends on the instruction, as we discussed. If it's I-type, for example, you should really use these bits to write to the instruction. If it's R-type, you should really use these bits to determine the ID of the register. Jump, branch, memory read, memory to write. Memory read, for example, is setting whether you're reading from memory. Memory write is setting whether you're writing from memory. Basically, based on the instruction you're executing, this control logic needs to be designed, and we're going to design that next. But before we go into that, let's take a look at how this branch is done, because I didn't show you exactly for you to finish, but let's finish it. So a branch needs to be executed using this read. You read two register values. So this ALU source needs to be set to 0 while a branch is executing clearly. And ALU control needs to be subtract or equality check, let's say. And branch condition is 1 if the equality check is true, basically, if the registers are equal for BEQ. So this condition is 1. And there we add another gate over here. If it's a branch, and if the condition is 1, then this multiplexer selects the branch address calculation ALU's output. And this other multiplexer selects that one if it's not a jump, basically. And this is not a jump, basically, because it's a branch equal. So basically, we need to pass the ALU results into the program counter, right? I mean, here we show 2 muxes. This particular picture shows 2 muxes, but it could have been a single mux, right? Controlled by 2 control signals. But you could also do that with 2 muxes, as you can see. Okay, so that's how you complete the branch data path. And then there's some ALU control logic that determines what control you do. And this is determined by the opcode, as you can see over here. Okay, so we're going to get back to this. We're going to actually have more fun with this one. But let's now design this control logic. We've kind of ignored the control logic, right? We've said somebody generates these control signals. Now let's generate these control signals, because you need to add the logic to generate the control signals as well. But it's going to be simple, hopefully, because it's really going to be a combinational function of the bytes of the instruction. So we know what instructions that we're considering. So I'm not going to consider jump register, JAL, jump and link register. We're going to consider only the R-type and I-type ALU, whatever we've seen, basically. And also we'll include some things that we have not completely seen, but it's okay. You can imagine those. So basically, these are branch not equal, branch less than or equal to 0, and greater than or equal to 0. We have not seen these exactly, but again, they're not that hard to think about. So we're going to have a single cycle control logic that's hardwired. And it's going to be a combinational function of the instruction bytes. So let's take a look at that. So we're going to generate the control signals in orange color. We're going to generate every single one of them. Yeah, that goes to these different places, as you can see. So regdest. Well, let's say, I think this is best done with examples. I don't want to go through all of these, but you need to basically look at all of the control signals and decide when they should be asserted and when they should be deasserted. Asserted means 1, deasserted means 0. Regdest is, remember, it's, okay, I need to find this. Yeah, this over here. Whether the destination register ID you're writing to is coming from bits 20 through 16 of the instruction, or bits 15 through 11 of the instruction. And we know, based on earlier experience, that if the instruction is R-type, we should be taking this one as destination register ID. And that's what this says, basically. Well, these are when it's asserted and when it's asserted. This opcode, if you check if the opcode is 0, that means the instruction is R-type. If you remember, well, this picture actually shows that. If the opcode is 0, then your destination register ID is coming from 15 through 11. For all other opcodes, it should be coming from here. And for these opcodes, it doesn't matter because you're not going to write to the destination register anyway. You're going to set some other control signal that's not going to do harm to the destination register. Does that make sense? Okay, so that's how you generate one signal, as you can see, right? It's a function of the opcode, and we know how to design this. It's an equality checker again. Well, it's a 0 checker. Actually, it's simpler than an equality checker. You could make it simpler. Okay, let's take a look at another one. Which one should we do? Maybe since we're talking about registers, let's do the register write. Basically, reg write signal, go back to the data path. Reg write signal is set to 1 if the instruction is supposed to write the register, set to 0 otherwise, right? Basically, decide which instructions are writing to the register and set the signal to 1 for those instructions, right? This is doing it the opposite way. Basically, these are the instructions that are not writing to a register, right? Make sense? Okay. Basically, if the instruction is not a store word or store instruction, if the instruction is not a branch, if the instruction is not a jump and jump register, we should be writing to the destination register. You could have done it the other way, right? You could have enumerated all cases where you're writing to the destination register, and you could have said it that way, right? So there could be multiple ways of doing this. Okay, so you can see that this is a combination logic again. It's a Boolean equation that we know exactly how to implement. Okay, so there are other signals like mem_read, for example. If the opcode is load, that is set, otherwise it's not set. So those are simple. Mem_write, if the opcode is store word, it's set, otherwise it's not set. So you can see that the control logic is very simple. Now, let's take a look at this one. This one is interesting because this is the multiplexer, PC source 2 multiplexer, this multiplexer over here, that selects whether you take PC plus 4 or the target of the address as computed by the conditional branch, this ALU over here. When do you select the next PC based on the 16-bit immediate branch target, that ALU? If the opcode is a conditional branch and if the branch condition is satisfied. Now you can see that that branch condition is satisfied is coming from the data path. That's not a function of opcode. You can see everything else, every other signal is a function of the opcode, except branch condition is satisfied, because you cannot make that decision just by looking at the opcode, because the opcode by itself is defined to be conditional upon the data, right? Okay, simple, right? Yeah, okay. Now, if you want to design, it's going to be very simple. But basically, the basics are very simple. I can go through all of these, but okay, let me go through one more. Mem_to_reg. We've seen this mux. This multiplexer is the mem_to_reg mux. Where do I find it? Anybody? Yeah, there you go. It's over here. This is the multiplexer, mem_to_reg mux. So you read either from the memory or the ALU result. Depends on the instruction, basically. So you decide who reads from memory, who reads the ALU result. Well, only load reads from memory, actually, and writes it to the destination register. So steer the memory output to the right port of the general purpose register file, only if the opcode is load word. So the control signal over here is determined by checking the top 6 bits of the instruction, which is the opcode, checking whether that is equal to the load word opcode, basically. That's it. So you do this for every single control signal. Okay. So clearly, I have omitted some of the other instructions over here. Clearly, a real machine's control signal is going to be, control logic is going to be much more, because we'll have a lot more instructions, right? And also more complicated instructions as well. Okay, so let's take a look at, let's have some fun with this data path, because basically once you have this data path and control logic complete, the rest is just about controlling the data path. Right? So let's take a look at how we control the data path using control signals when we have an R-type ALU instruction. Basically, you set the appropriate control signal, right? R-type ALU, this is the destination register. So it should be set such that you select this, you connect this data input of the mux to this output. We are writing to a register in R-type ALU, if you remember. We're reading from a register because it's R-type. 2 registers need to be added. And the function is specified by those func bits. Remember those func bits? There needs to be some logic that takes those func bits and process it, generates the ALU operation. We're doing no harm to memory, not reading it, not reading from it, not writing to it. But we need to set the mem_to_reg signal appropriately so that we get the ALU results into the destination register, which we're writing to, as we discussed earlier, right? And we need to increment the PC by 4. So we set these muxes appropriately such that PC plus 4 nicely flows through into the PC, right? So basically, you can see that control, you can now see the control function of the control signals. Control signals are controlling the data path to appropriately flow the data to the appropriate places as specified by the instruction, right? Control signal is really orchestrating the data flow in the machine. Hopefully that's clear, right? By connecting these components the way I connected, we're orchestrating the data path to do the right thing for that instruction, R-type ALU. So if you want I-type ALU, you don't do this, you do this. And you can have fun like this, right? Basically, I-type ALU, as we discussed, the second operand is coming from this multiplexer, sign extended 16-bit immediate. And you always add, well, how do we get to load word? Sorry, yeah, that's why you should not always add. You should have an opcode, basic opcode specifies what you do in the ALU. You do no harm over here. That's why this didn't change. Basically, this is the only thing that changes between R-type and I-type ALU, as we have seen earlier. The destination register comes from a different place, basically. Okay, load word is very similar to I-type ALU. Now, going from I-type ALU to load word, you see what changes, right? This opcode becomes only add because we're calculating address, and we read from memory, and the data should come from memory output to be written into the destination register. So I-type ALU, load word. I-type ALU, load word. Makes sense, right? So store word is very similar to load word, except a few things change. Basically, remember what we said is you invert what you do in memory, you store, not load, and you don't write to the register file. So these control signals get negated, as they did. And some things we don't really care about. We don't really care because we're not writing to the register, right? Store word doesn't write to the register. Okay, let's take a look at branch not taken. So a branch not taken looks like this, basically. What do we need to do over here? We're not writing to the register. We're not writing to memory at all, reading from memory at all. We're calculating the branch condition. So there needs to be a way of calculating the branch condition based on the opcode of the branch. It could be branch equal, branch not equal, etc. But this is not taken case. Not taken case meaning the branch condition says this should not be taken. So this is 0. So this over here says that this is 0. So you should really select here. So PC plus 4 again needs to flow over here. But you see that now the output, the control signal over here is dependent on the data, right? Okay. If it's the branches, basically some control signals are dependent on the processing of data, as we've discussed. If the branch is taken, the only thing that's different is this multiplexer, how this multiplexer is controlled, right? You can see. And that multiplexer is controlled based on this AND gate over here, because if the branch is taken, this AND gate will evaluate to 1, so that we select the output of this target address adder, or target address adder, and that should flow into the program counter. Okay. Okay, jump is actually very similar to branch not taken, except there are a lot of things we don't really care about as well. It's not exactly very similar to branch not taken because you actually calculate the address in a different way, as you can see. But jump is do no harm in this part of the data path that you don't really care about, and just take the concatenated address that you calculate into the program counter. Okay? So basically, controlling the data path is done through control signal generation, and control signal generation, we've already seen, is done through this. You need to go through every single instruction and figure out how to generate every single control signal. Okay, so you can have more fun on your own also with this. Okay, so let's talk about how this control signal generation is done. I've given you already the hardwired control. Basically, control signals are generated combinationally based on bits in the instruction encoding, plus some bits that you need during data path processing, like in conditional branch. But you could also do it sequentially, and we will see that later on, not today. Basically, you can have a memory structure that contains a control signal associated with an instruction. This is called a control store. And both types of control structure can be used in single cycle processors, actually. You can imagine you index using the opcode, a memory structure that gives you all of the control signals that you need, right? It's kind of a lookup table, right? Instead of implementing everything hardwired, just like we did, you just use a lookup table. Based on the opcode, you get all the control signals, right, that are needed for the instruction. And in existing processors, both types of control structures are actually used. Some of the control signals are stored in a memory structure. Some of those control signals are generated hardwired, depending on the latency of each structure and how much the critical path, how much on the critical path the control signal generation is, etc. So that was our complete single cycle processor. Let me very quickly go through what you're going to read in your book. Basically, your book builds something very, very similar. As you can see, there's not much difference. A lot of the things are similar. This is also MIPS. But let's take a look at one thing. So for example, for the data path, let's take a look at load in this particular case. How do you build a data path for load? You need to connect the program counter to instruction memories. You get the instruction. And then you need to read the source operands from the register file. In this case, the first register. And you need to sign extend the bottom 16 bits of the instruction, get the immediate sign extend immediate. These are the two sources that are needed for an I-type instruction, as we have seen, right? That's the load word. And we add them together, set the ALU control appropriately. ALU result gets connected to the data memory. And then the read data needs to get connected to, read data coming out of memory needs to get connected to the destination register data value. And the destination register ID should be set using these bits of the instruction, and the register write signal needs to be set. Basically, it's doing exactly the same thing that we have seen in a different way with different wording, let's say. And of course, you also need to determine address of the next instruction. So you need to add the PC plus 4 adder. We also added in the processor that we studied. And your book also designs the control unit, and this is how it designs the control unit, as you can see, depending on the instruction type. Of course, BEQ also needs additional control logic. That's part of the data path processing. And this is the complete single cycle processor from your book, which is very similar to what we just studied. So I think I'm going to conclude with your reading assignment. So if you understood everything right now, that's great. If you still want to understand more, please read the lecture slides and backup slides. There's also backup slides. And the readings from your H&H book will certainly enable you to internalize these better. But this is what we developed in lectures, and this is the single cycle microarchitecture in your readings. In the next lecture, we're going to start with evaluating this single cycle microarchitecture and talk about why this is not a good idea. And then we're going to do something better. But we don't want to do that today or tomorrow. We'll do that next Thursday. Okay, take care. Have a good weekend.